So now some interesting things happen when we apply Lenz's law to devices working at microwave frequencies. Lenz's law normally applies in situations where the wavelength of the rate of rotation, say I'm rotating a rotor at 1 second, 1 cycle per second, or frequency 1 hertz. The distance from the stator coil to the permanent magnet is going to be much less than the distance it takes that electromagnetic field to radiate during a time period of 1 second. So the reflected load from the amount of current the light bulb is drawing back into the rotor to affect how hard it is to turn a rotor is almost instantaneous. But now we can do the same thing in microwave frequencies, and something different will happen. If you take a single nanocrystal sized magnetic particle and you cause all of its electrons to precess in phase at microwave frequencies, then it is sending out an electromagnetic field that rotates just as if I had a very small permanent magnet rotor of a motor generator. So that rotating magnetic field is capable of inducing current flow. In this case, I won't have a stator winding, but rather you can use microwave reflector antennas that are also tied to a load. Or to give an even more basic example, instead of a stator coil, a single stator coil or loop, you can imagine that you have a whole bunch of loops all around the rotor, and they're all shorted together. So it's just like one big loop with a short. So the maximum amount of current flow will be possible through that coil, which is actually not a coil anymore, but just a spherical chamber in which that single rotating field is at the center. So the maximum amount of current induced in that will reflect back magnetic fields which would normally oppose the motion of that rotating magnetic field at the center. If there's any amount of resistance to that spherical cavity, because it's not a superconductive material or whatever, then the energy dissipated in the form of heat through the resistance of that reflecting material should be reflected back and cause resistance to the motion of the magnetic field that induced that current flow. But at microwave frequencies, it takes a certain amount of time for the electromagnetic field from the rotating precessing electrons, rotating magnetic field from the precessing electrons. It takes time to reach that cavity wall, and it takes time for the induced current's magnetic field, which would normally be in opposition, to reach back to that rotating magnetic field at the center. And it is possible to obtain a size of cavity such that the time delay of the rotating magnetic field to that surface and the time delay of the reflected opposition magnetic field back to it is such that by the time it reaches back, it is already at a point in time where the rotating magnetic field is made at least 90 degrees or probably closer to 180 degrees rotation already in the orientation of its magnetic field, such that the reflected signal coming back no longer opposes that motion but rather aids that motion. Another way of looking at it is And if you have a sample of ferromagnetic material, a very, very small, just a single nano-sized crystal of magnetic material, and you stimulate electron paired magnetic resonance, or I should say ferromagnetic resonance in that material, then it's radiating out a rotating magnetic field at its precession frequency. And if I reflect that right back into it, then my reflected signal back into it can now act as the stimulating source for ferromagnetic resonance, rather than continuing to use any other external microwave antennas to stimulate that ferromagnetic resonance. I can use its own emissions to continue to stimulate it, to continue to have ferromagnetic resonance at that particular frequency, which is the natural resonant frequency as established by the field strength of an external magnetic field.